So let us then embark today on a new aspect of signals and systems, which aims to generalize some of the things that we've been looking at over the past few weeks. Let us look broadly at what aspects of signals and systems we have opened up, or we have tried to bring forth in our discussions over the past few weeks. Initially, we looked at the idea of signals and systems entirely in the domain in which they were described, most commonly time. Right? So we looked at the description and the analysis and the characterization of signals as also systems purely from their descriptions or their behavior in the original domain, time, space, or a mixture of time and space. Yeah. Subsequently, we went on to making an important distinction between continuous and discrete variables. Right? There is a fundamental difference between continuous and discrete variables. We brought that out in a most generalized sense, and then we made it more tractable by confining our attention to the situation where the discrete variable was obtained by uniformly sampling the continuous variable. Okay, and that's the case with which we dealt in great detail. So we had, by and large, two important classes of systems and also signals: continuous space or time signals and systems, and discrete space or time signals and systems. Yeah. Further, we looked at the possibility of changing the domain of analysis. So instead of looking at the same domain in which the system or the signal inherently is described or works, we looked at the possibility of an alternate domain. And we spent quite some time on discussing the Fourier domain, right? The Fourier transform, which is based on the idea that one can think of signals as comprising of many sine waves superposed with appropriate amplitudes and phases, and a corresponding change in the way in which we look at systems results. Some of the operations that are fairly complicated in time or in space become much simpler when we think of them as operations in the Fourier domain. Convolution is an important example. The operation, the effect of a linear shift invariant system on a signal is sometimes easier to see in the frequency domain. Sometimes, I am not saying universally, but sometimes. Right? So there is a choice available to us. If the Fourier transform of a signal and also the impulse response of the linear shift invariant system is defined, then it becomes convenient in some situations to use this choice to do one or the other, to work with the system or the signal in time or in frequency. Right? Later, we looked at the relation between continuous and discrete time signals by building up the idea of sampling. In fact, we addressed the question, are there situations in which we can have an equivalence between a continuous time signal and its samples? And we found that if the continuous time signal is band limited, then there is such an equivalence. So one can deal equivalently with the samples of the continuous time signal taken at a sufficient rate, which was equal to twice the maximum frequency component for a real signal, right? And we could reconstruct the original signal perfectly. So whatever we wish to do with the original continuous time signal could equivalently be done with the samples. And that brought us to the idea of digital signal processing, right, towards the end of the previous lecture. We also looked at various options, by the by, to reconstruct a signal from its samples, provided that reconstruction is possible, both exact methods and approximate methods based on holes. Yeah? And now we take this discussion further by embarking on a new direction in signals and systems, namely looking at broadening the scope of an alternate domain. You see, we kept emphasizing that the Fourier transform needs to be defined in order that one use the Fourier transform in one's analysis. So unless the signal satisfies the Dirichlet conditions, the Fourier transform is not defined. And other than pathological signals, it is not too difficult to think of meaningful realistic signals which disobey the Dirichlet conditions. To take an example, an exponentially growing signal which occurs very commonly in meaningful system analysis experiences is not Fourier transformable, right? And therefore, we need to build up a more general framework both for continuous time and for discrete time systems, which will allow us to work in a domain other than the domain in which the signal or system is defined, right? So our aim in today's lecture is to build up this concept of an alternate domain, a more general domain for analyzing signals and systems both in continuous time as also in discrete time. Now, to carry out this task, it would once again be expedient to look at the linear shift invariant system, right? And this time we will take inspiration from what the Fourier transform does for us. The Fourier transform makes the operation of a linear shift invariant system very easy to describe, right? It becomes memoryless in the Fourier domain. Can we have a more general kind of a transform, if we might want to call it that, which takes this property even for signals for which the Fourier transform is not defined? Of course, it may also work for signals whose Fourier transform is defined, but we'd like to carry the domain further, right? So let's look at a linear shift invariant system. And first, let's look at a continuous linear shift invariant system. With impulse response ht. We shall start by asking the question, just as the complex exponential, just as the rotating phasor formed an eigenfunction of the system under certain conditions on the impulse response, essentially the Dirichlet conditions, is there a more general form of the eigenfunction for the linear shift invariant system? In fact, we can answer the question at least partially by looking at the form of the expression of the rotating phasor, e raised to the power j omega t. Here, you might now think of j omega as restrictive in the sense that it looks at only a part of the complex plane. It looks only at the imaginary axis. So what if we were to take this to the whole of the complex plane? Right? Suppose we were to use not just the imaginary axis, but allow, the parameter here to be a complex variable s. And we were to investigate the effect of the system on this function, e raised to the power of st. So let's look at the output in this case. Yeah, so yt, of course, would be the convolution, and this time we shall choose to write the convolution in the following way. which we can rewrite in the following way. This is provided this integral converges. This is provided this integral converges. So what is the conclusion that we draw from here? The input is e raised to the power of st. The output is e raised to the power of st times a constant that depends on s. Of course, we assume here that this integral converges. But we shall see in a minute that the class of ht for which this integral converges, at least for which one can find a range of complex numbers on which this converges, is much larger than the class of S, or the class of ht for which the Fourier transform converges. Right? So it's a much wider range of functions that we are talking about here. Now, let's see. So in fact, if we look at this expression, it's a function of S. And interpreted in a different way, it's an operation on the impulse response. Right? There are two different ways of understanding this. One thing is that it's a function of S which multiplies this e raised to the power of st when it goes into the LSI system. And therefore, we shall call this the eigenvalue corresponding to this eigenfunction. So this is a more general form of an eigenfunction. Recall that the word eigenfunction refers to a function or a signal which goes into the system and comes out unchanged in form. The word eigen in German, as I told you, refers to own, one's own. So the LSI system's own function, eigenfunction, right, which comes out unchanged. This is a more general form of an eigenfunction of an LSI system. And the corresponding eigenvalue is given by this, right? So naturally, we wish to investigate what is more general, or under what circumstances this eigenvalue converges. Now let's look at the expression of the eigenvalue. You see, the eigenvalue here, which we shall denote by capital H of S, can also be thought of as an operation on HT. You see, you can think of it. See, as I said, there's another way of looking at this relationship. One can think of this relationship as a mapping from the time domain to some other domain defined by the variable S. So you see, it's quite possible that for some values of S in the complex plane, this particular expression converges, and for others it does not. So we must allow that possibility. And we must also be able to find out the conditions on S for a given H for which this converges. Alright? If we look at the expression, what are we saying broadly? You see, let's first understand what is it that will affect convergence. You see, it is, if you look at absolute convergence, and that's what we are interested in. Absolute convergence means the convergence of the absolute value of the integrand, right? The absolute value of the integrand here is the same as mod h lambda times e raised to the power minus sigma lambda, where sigma is the real part of S. Yeah? I mean, the modulus of e raised to the power minus s lambda is also equal to the modulus of e raised to the power of minus sigma lambda, where because the modulus of e raised to the power, whatever is the imaginary part of s yields a magnitude of 1, e raised to the power. So, if s is equal to sigma plus j omega, then the term e raised to the power minus j omega lambda has a magnitude of 1. So, it contributes nothing to the magnitude. Yeah? So, you see the convergence is going to be affected by this. The absolute convergence of this integral is going to be affected by this. So, one clue that we discern from here is that the convergence or otherwise of this integral is likely to depend very strongly on the real part of S. Yeah, it's likely to depend very strongly on the real part of S. And in what way is it going to depend on the real part of S? You see, what is this term doing? Actually, if you look at the capturing factor e raised to the power minus sigma lambda here, it is introducing an exponentially decaying term to allow convergence. So, even if h lambda has an exponentially growing term, this e raised to the power minus s lambda can introduce an exponentially decaying term to enable convergence. That is the flexibility offered in this HS as opposed to the Fourier transform, where you have no such provision for capturing exponential growth. So, it is very clear that any HT which can always be majorized or bounded by an exponentially, just an exponentially growing envelope, can be forced to come down to convergence by using this operation. So, it means the growth of HT, if it is assured that the growth of HT can be captured by an exponentially growing envelope at worst. That means the worst case as far as HT goes is that it grows exponentially. What could be worse than that? Suppose it grows as e raised to the power of t squared. You see, e raised to the power of t squared is worse than exponential growth. So, we cannot call it, it's not possible to capture or to majorize e raised to the power of t squared by an exponentially growing term. But on the other hand, e raised to the power of t, in fact, e raised to the power of at for any constant a, e raised to the power of at for any constant a can always be captured by an exponentially growing term. In fact, e raised to the power of e raised to the power of real part of a into t, right? That's the envelope within which this lies, right? So, what it really means is that this broadens considerably the class of HT for which we can assure convergence here. And we give this operation, as I am saying, we could think of this as an operation or as a transform on the function HT. We give this transform a name after the mathematician who, sort of brought it to focus. We call it the Laplace transform. So, this shall be called the Laplace transform of the function HT. And actually, we have seen the Laplace transform is never specified entirely by an expression. Well, let us take an example. Let HT be equal to e raised to the power of 2t ut. Now, clearly this function has no Fourier transform because it's not absolutely integrable, right? But let's investigate whether it has a Laplace transform. Indeed, if we calculate h of s, it's e raised to the power of 2 lambda, e raised to the power minus s lambda. I mean, I don't need to write d lambda. And this integral runs from 0 to infinity. Alright, so I write this as e raised to the power 2 minus s lambda d lambda, integrated from 0 to infinity. Now it is very clear that this expression, would either converge or diverge depending entirely on the real part of 2 minus s, right? So in fact, if the real part of 2 minus s is negative, if the real part of 2 minus s is negative, this integral would converge. On the other hand, if the real part of 2 minus s is greater than or equal to 0, it's non-negative, it would definitely diverge. Right? It's very easy to see because the imaginary part has no effect on the convergence or divergence. Yeah? And therefore, this is the condition of convergence. Which boils down to saying that real part of s must be greater than real part of 2, which is of course 2. So let's sketch the region so now you see s is a complex variable, so we could think of the complex plane and a region in the complex plane in which this convergence can be effected. So let's sketch that region. This is the region. So the shaded part is the region of convergence. Now I assume that an exposure to networks or the analysis of electrical networks would also have exposed you to the Laplace transform. And some of these ideas would already be familiar. But our aim here is also to take this analysis to discrete time systems and also to bring forth the properties of the Laplace transform that are universal to LSI systems, not just to networks. Right? So let us ask two questions now. Before we look further at the possibilities of region of convergence and so on, let's ask two important questions. One question is whether the convolution property carries over to the Laplace transform domain. That means, another way of putting it is, if I put an input xt into an LSI system, and just as I can define the Laplace transform of ht, I could also define Laplace transform of xt and the output yt. Can I relate the Laplace transform of the output, input and the impulse response of the LSI system in general? Let's investigate that question first. And the second question that we shall pose is, how do we carry out this generalization to discrete time systems. All right. So let's take up both the questions in that order. First question. I have a continuous time system with impulse response, continuous time LSI system. The impulse response is ht. The input is xt. The output is yt. We shall use the following notation to denote the Laplace transform. We shall write a script L and xs here to denote the fact that the Laplace transform of xt is xs. Now I must emphasize that a Laplace transform is never merely an expression. In fact, in the previous example, let us complete that discussion just for sake of understanding this point. You see, for e raised to the power of 2t ut, we found that the Laplace transform converged when the real part of s was greater than 2. And what did it converge to? It converges to integral 0 to infinity e raised to the power 2 minus s lambda d lambda, which, as you can see, is e raised to the power 2 minus s lambda divided by 2 minus s, lambda running from 0 to infinity, which comes out to be 1 by s minus 2. And the region of convergence is the real part of s greater than 2. It is very important to emphasize that the Laplace transform of this ht is both this and this. Yeah, it's always both an expression and a region of convergence. We shall see further why this is the case as we go deeper into the analysis of the Laplace, also the other transform that we are going to build. So let's assume that the Laplace transform of the input is xs, and the Laplace transform of ht is hs, and the Laplace transform of yt is ys. The first question that we wish to address is there a relation between them? So in other words, let's express ys in terms of yt, and then we shall express yt in terms of xt and ht and see if there is a relationship. Yeah? So let's first write down the expression for ys. Y of s, by definition, turns out to be minus infinity to plus infinity yt e raised to the power minus st dt. Of course, here I have replaced the variable of integration by t instead of lambda. It makes no difference. Yeah? And I write yt in terms of the convolution integral. So I write minus infinity to plus infinity. Again, integral minus infinity to plus infinity. You could write h lambda xt minus lambda d lambda. E raised to the power minus st dt. Yeah? Now here we have a twofold integral, a double integral on lambda and on t. We'd like to convert it to a twofold integral on two other variables which are more convenient, because we have a t minus lambda here. So we'd like to have two variables, lambda as it is, but we'll replace t minus lambda by another variable phi. So instead of an integral in terms of d lambda dt, we'd like it to be an equivalent integral on d lambda d phi, where phi is t minus lambda. Yes, we'd like to make this transformation. Now I leave it to you to make this transformation. All that you need to do is to take the Jacobian of this function t. So you have the Jacobian matrix would be 1 minus 1, 1 and 0. Its determinant would be 1. Its determinant, the magnitude of the determinant would be 1. So therefore, d lambda dt is equivalent to d lambda d phi. And of course, the limits have to be put properly. But when lambda and t individually vary from minus infinity to plus infinity, the range in which lambda and phi vary is also minus infinity to plus infinity. So therefore, this entire double integral can be rewritten in the form minus infinity to plus infinity, and again minus infinity to plus infinity, h of lambda, x of phi. And my task now is to eliminate t here. T clearly becomes lambda plus phi. So e raised to the power minus s lambda plus phi, d lambda d phi. So much so for the double integral. And now we can very easily, you see, if you notice, this term e raised to the power minus s lambda plus phi can be rewritten as e raised to the power minus s lambda into e raised to the power minus s phi. And then we have a separation of variables. There are some variables there are some terms here that depend only on phi, and there are some terms that depend only on lambda. We can collect the integral on lambda inside. So we can rewrite this as minus infinity to plus infinity h lambda e raised to the power minus s lambda, and then inside we may have minus infinity to plus infinity x phi e raised to the power minus s phi d phi, and the whole d lambda. Yeah, this is how we can recollect this integral. Yeah. Now look at this expression. This is the Laplace transform of xt evaluated at s, provided it converges. Right? Now let us assume that we choose a value of s for which this converges, right? And later we shall put a further constraint on s. For the moment, we want an s for which this converges. So this would be equal to capital X of s, and since then it is independent of lambda, I can bring it out, right? So this becomes x of s, leaving the rest of the expression here, integral h lambda e raised to the power minus s lambda d lambda, but that's equal to the Laplace transform of h evaluated at s again, provided it converges. So now what do I want? I want those s for which both of them converge. Suppose I choose an s which is in the intersection of the region of convergence of xs and hs. Then I might write this down as xs times hs. Of course, I must emphasize this condition is sufficient but not necessary. If S belongs to the intersection of the region of convergence of x and h, of course this integral would converge, or this separate product would converge. But it could happen that the causes of non-convergence of this might be cancelled by certain qualities of this. So in this process, the region of convergence could sometimes broaden, which means, you see, if we look at this, what does it tell us? It tells us that Ys, you see, it tells us, what is our conclusion? Let's draw conclusions one by one. Important conclusion. The important conclusion here is that Ys is equal to Xs Hs, and the region of convergence of Ys is at least equal to means it's a superset, right? It definitely includes the region of the intersection of the region of convergence of X and the region of convergence of H. Yeah, so this is what we conclude. A very important conclusion. If there is a non-null, if there is a non-empty intersection of the region of convergence of X and H, at least that non-empty set is a region of convergence for the Laplace transform of the convolution. But the region of convergence could be broader, and that would happen because if you look at the expression there, the causes of non-convergence in one of the integrals could be overcome by the other integral. That could happen, right? At this point in time, I am not qualifying this too much more, right? We are just leaving it at that. We are observing that a very important property that we had for the Fourier transform carries over to the Laplace transform. Namely, that the operation of convolution becomes memoryless in the S-domain, right? The Laplace transform of the input is multiplied by the Laplace transform of the impulse response to get the Laplace transform of the output. And just as we had given a name to the Fourier transform of the impulse response for an LSI system if it exists, we shall now give a name to this quantity Hs. Because this quantity Hs is a universal descriptor of that system in some sense. Yes, it tells me that the ratio of the output Laplace transform to the input Laplace transform, yes, it tells me that Ys divided by Xs is equal to Hs independent of Xs. So it's a universal descriptor of that system, and we give it a name. We call it the system function of the LSI system. Where are we now? We are on a slightly broader plane than the Fourier transform. For example, an LSI system whose impulse response is e raised to the power of 2t ut will not have a frequency response, but it will have a system function. Needless to say, the convolution description is the most general for an LSI system. Among those that we have discussed, the next most general is the Laplace transform or the system function. And the least general is the Fourier transform. Yeah? In fact, let us now go further. Can we relate the Fourier transform and the Laplace transform? If a relation exists, that means if the Fourier transform of the function is defined and if the Laplace transform is also defined, can we relate them? Yeah? Well, what do we mean by the Fourier transform being defined and the Laplace transform being defined? It just means that, you see, if you look at the expression for the Fourier transform of Ht, for example, if this is defined and the Laplace transform, of course, is definitely defined, then for, that means if this is defined, then HS definitely converges on the imaginary axis. So what does it mean? It means the Fourier transform is the Laplace transform evaluated on the imaginary axis. Yeah, so the Fourier transform is the Laplace transform on the imaginary axis. All right. What does it mean? In order that both be defined, the imaginary axis must be a part of the region of convergence of the Laplace transform. Yeah? If both the Fourier transform and the Laplace transform are defined, then the imaginary axis must be a part of the region of convergence of the Laplace transform. So we've answered the first of the two questions that we raised, right? Namely, is this important property of the Fourier transform, namely convolution carries over to multiplication in the Laplace domain, valid? It is valid, right? The second question that we asked is how do we carry out this generalization of eigenfunctions to discrete time, right? In other words, just as we found the most general eigenfunction for a continuous time system, what is the most general eigenfunction for a discrete time system? Right? So we'll address that question the next. Let's take inspiration from the continuous time case. Last time we had looked at the Fourier transform, or the discrete time Fourier transform of a sequence, right? We had defined the discrete time Fourier transform of the sequence xn as the function capital X of capital omega given by a summation xn e raised to the power minus j omega n. Yeah, this was the discrete time Fourier transform, the sequence, provided the summation converged, right? Now, of course, we had at that point not carried further the discussion on properties of the discrete time Fourier transform, and the reason is that I'd like to do that together with the generalization. So rather than do it separately for the discrete time Fourier transform, let's find a more general transform for discrete time systems, as we are doing for continuous time systems, which allows us this kind of transform domain representation, and then make particular comments for the DTFT. Yeah. So you see, taking inspiration from the discrete time case, from the continuous time case, what is it that enabled us to go from e raised to the power j omega t to e raised to the power of st, looking at the whole complex plane, right? So here you see, the idea is that, if you look at this expression, you can think of e raised to the power of j omega n as a sequence, right? And xn is of course a sequence. So you see, this quantity that we have is actually a dot product between the sequence xn and e raised to the power of j omega n. If you recall, we had defined the dot product between sequences as taking the product of the corresponding points on one sequence and the complex conjugate of the points from the other sequence, right? So in a way, this is a projection of the sequence xn onto the sequence e raised to the power of j omega n. Now what is e raised to the power j omega n? Of course, I'm sorry, here there must be a correction. This must be capital omega, yeah? A small correction. Here we need to have a capital omega. Now that's, because we've used a different variable name. Now, you see, the point is that the sequence e raised to the power j omega n is a sample version of the sequence e raised to the power j omega t. Yeah? So what does it mean to generalize this to more general eigenfunctions? It might be wise on our part to look at a sample version of e raised to the power of st, right? What do you mean by a sample version of e raised to the power of st? Let's write it down. You see, a sample version of e raised to the power of st would look like e raised to the power of Sn capital T, where T is the sampling interval. Yeah? So we may rewrite this as e raised to the power of st times, raised to the power n. Is that right? We might rewrite it that way. But after all, what is e raised to the power of st? E raised to the power of st is a complex number. If s is a complex number, e raised to the power of st is in general a complex number. In fact, it is not too difficult to show that as you carry s all over the complex plane, you also span, if you think of this as a composite complex variable, let's call that complex variable z. So we rewrite this as z raised to the power of n, with z equal to e raised to the power of st. As you carry s all over the complex plane of s, z would also run all over the complex plane z. In fact, we'll see later that we need only a part of the s plane to cover the whole z plane. Yeah, we shall see that. We need only a part of the s plane to cover the whole of the z plane. Yeah, we shall see that later. At the moment, we are assured that the range, if you think of this as a mapping between s and z, right, then if you allow the domain of S to be the entire complex plane, the range is also the entire complex plane of Z. It's a different matter that with even a smaller domain in S, you will still have the same range on Z, namely the whole complex plane. We'll look at that later. But definitely, if you allow S to range over the whole complex plane, it will cover the whole complex plane Z, right? So, what it really means is, we now need to look at the possibility of sequences of the form z raised to the power of n, where z can take on any particular complex value. And let us investigate what happens when this sequence, z raised to the power of n, passes through a discrete time linear shift invariant system. So let there be a linear shift invariant system with impulse response h of n. And let us put in z raised to the power of n as an input to this system, where z is any complex number. We shall later on restrict our class of complex numbers when we discover what the output is like. Of course, the output would be the convolution of the input with the impulse response. We shall write a convenient expression for the output, summation k, going from minus infinity to plus infinity, hk z raised to the power n minus k, a discrete time convolution. Yes? Now z raised to the power of n minus k can be rewritten as z raised to the power of n into z raised to the power minus k. And therefore, this might be rewritten as summation k going over all the integers hk z raised to the power minus k, the whole multiplied by z raised to the power of n. Z raised to the power of n is independent of k. Yeah? Now, this expression is a function of z, only of z. And as before, we expect that for certain z it might converge and for certain z it may not converge. Now, convergence will definitely depend on the absolute value of the summand. Right? It would depend on the absolute value of the summand here. And what is the absolute value of the summand? The absolute value of the summand is mod hk z raised to the power minus k, which is nothing but mod hk times r to the power minus k, where r is the magnitude of z. Is that right? Yeah? So here we notice that we have again an exponentially varying sequence which attaches itself to hk. And this summation would converge as long as this exponentially varying sequence can capture the growth of hk. Yeah? For example, even if hk is exponentially growing, still this might converge if the exponential decay of this is faster than the exponential growth of this. Alright? So take for example the case where hk is equal to 2 raised to the power of k. Yeah? Now we'll use the case hk is equal to 2 raised to the power of k uk, where of course uk is the standard unit step sequence defined by 1 for k greater than or equal to 0 and 0 for k less than 0, right? Now clearly in this case this quantity summation on summation on k hk z raised to the power of minus k becomes summation k running from 0 to infinity 2 raised to the power of k z raised to the power minus k. Right? This can be rewritten as summation on k running from 0 to infinity 2z inverse raised to the power minus k. 2z inverse raised to the power k. Alright? Now you see, you notice this is a geometric progression, and the geometric progression is an infinite geometric progression, and it would converge if the common ratio is less than 1 in magnitude, right? So therefore this would be equal to 1 by 1 minus 2z inverse, provided mod 2z inverse is strictly less than 1, right? Which means mod z is greater than mod 2 or greater than 2. So in fact, just as we had a region of convergence in the S-plane, we also have a region of convergence in the Z-plane. right? This is the region of convergence. For this particular case, this is the region of convergence, mod z greater than 2. Also notice the difference in the nature of regions of convergence. In the S-plane, the regions of convergence related to the real part of S. In the Z-plane, the regions of convergence relate to the magnitude of Z. That's because the convergence in the S-plane depends on the real part of S. The exponential growth or decay depends on the real part of S, whereas here it depends on the magnitude of Z. So, now we shall give this a name.
So,
yes?
In a sense, there is conversion from Cartesian to polar coordinates.
Yeah, that's right. The question is, this is like a conversion from Cartesian to polar coordinates. That's correct. Because, there's a mapping Z equal to e raised to the power of st. So, that's a mapping in a sense from Cartesian to polar coordinates. That's right. So, there's a kind of mapping from Cartesian to polar coordinates. Anyway, coming back to this, we shall give this a name. We shall call this the Z transform. Just as we call that the Laplace transform, we shall call this the Z transform of 2 raised to the power of k uk. And once again, notice the Z transform is never just an expression. It is an expression with a region of convergence. Right? A Z transform is always together with a region of convergence. Yeah? Finally, now that we've given this a name, what was our conclusion earlier as far as the input Z raised to the power of n to the system is concerned? Our conclusion was that when you put in Z raised to the power of n into an